Hello there. Welcome to another edition of Mr. Weis solves a not exactly random, but solves an AP problem. This is one of the AP problems from our homework. So let's get started. This is problem number from 2013, problem number 5. And it begins by asking us to consider the following differential equation. dy dx equals y squared times the quantity 2x plus 2. This is in fact a differential equation. It's an equation that involves the derivative. The solution to such a differential equation would mean finding a function or a bunch of functions that happen to make this equation true. We would be looking for a function whose derivative is equal to its self squared times 2x plus 2. And it would be a function, y as a function of x. Now they're saying, let's give a solution to such a differential equation a name. Let's say that y equals f of x is the particular solution with the initial condition that f of 0 equals -1. It turns out that there is only one such function. There is only one function whose derivative, a function with respect to x, whose derivative is equal to itself squared times the quantity 2x plus 2, and which happens to go through the point 0, -1. So they're saying let f of x be the name of such a solution. Perhaps by the end of this problem, we'll actually figure out what f of x is. We'll see. Part A, though, a little bit strange. Part A asks us to solve a limit. Part A says compute the limit as x goes to 0 of f of x plus 1 over sine of x. That's what it asks. All right, weird it's asking for a limit problem, but this is very common in these AP problems. They're very good about connecting a lot of different areas. This presumably is about a differential equation, and yet we're being asked a limit question. Okay, so limits. First thing I always try to do when I find a limit is I try to plug in the value that the x is tending towards and see what happens. So f of 0 plus 1. Well, f of 0 is -1, so we're getting -1 plus 1 over sine of 0, which is also 0. So, oh boy, we have ourselves an indeterminate form. And this means we have all sorts of tricks that we might try to do when we're solving limits. In this case, I believe the trick is your favorite trick, the hammer that you like to hit every indeterminate form limit problem over the head with, which is L'Hopital's rule. L'Hopital's rule says that this limit is the same as the limit you get when you take the derivative of the top and the bottom of this fraction separately. So the derivative of the top would be called f prime of x plus 0, and the derivative of the bottom would be cosine of x. Okay, so now we simply have to figure out what f prime of 0 is. We'd like to plug in again. If we plug in 0, we're going to get a 1 in the denominator. That's fantastic. And we have to figure out what f prime of 0 is. So that's our question right now. What is f prime of 0? Okay, well, f prime is dy dx. So what we're really asking for is, what is dy dx when x equals 0? That's what we want to know. Well, dy dx ends up equaling this expression right here. And we know that dy dx when x equals 0 is whatever y equals when x equals 0 times 2x plus 2, where the x ends up being 0 as well. So remembering that when x is 0, y ends up equaling -1. This ends up being -1 squared times 2 times 0 plus 2, which, when all the smoke clears, is just 2. And therefore, we can plug back in all of this stuff up into here, and we find out that this therefore equals 2 over 1, which is 2. And that's the answer to the first part of this problem. Okay, so here we have part B of this problem. Part B asks something a little bit more familiar, something a little bit more recent. Differential equations. And what it wants us to do, the same differential equation, it wants us to use Euler's method using exactly 2 steps to try to estimate what f of 1/2 is, starting with the fact that we know what f of 0 is. Okay, so quick review on how Euler's method works. Euler's method often is presented as if there's this list of facts you're supposed to know, or this chart you're supposed to make. And honestly, if you're doing some stuff on a computer, these charts can be super duper helpful. But when you're doing only 2 steps like this, I don't even remember what the chart says. I understand the idea of how Euler's method works. And here is the idea. I'm going to draw a little picture to try to show what we're doing. So here is my picture. What this is going to try to be is a graph of f. F is a particular function. It's the solution to this differential equation that happens to pass through the point 0, -1. So here we are at 0, -1. Now, I don't know what f looks like. I don't really have any idea. I'm just going to kind of draw something, okay? Perhaps this is what f actually looks like. So who knows? I'm just drawing something here. Maybe f looks something like that. Maybe this is f of x. So let's say that this right here is 1/2. So what we are attempting to estimate right now, what we want to figure out is what this point right here is. This point would be 1/2, f of 1/2. And we want the y coordinate of this point. We would like to estimate what that is. But again, we don't know what f of x looks like. We have no idea. Because we have not solved the differential equation. But we do know some stuff. We know that, for example, we know that f passes through this point right here, 0, -1. We know that from the initial condition. And we also know something about the derivative right here. So we know from part A, actually, we know that f prime of 0 is 2. In other words, we know that the slope of the tangent line to this function at x = 0 is 2. So that slope is 2. We can use that slope to therefore find instead of moving along the function here, we can move along this tangent line and try to figure out, here we are at 1/4. We can figure out what this point right here is. This point's x coordinate is 1/4. We need to figure out what the y coordinate is. And then what we're actually going to do, and this is very interesting, is we're then going to not be talking about f anymore. We're going to instead talk about the particular solution to this differential equation that happens to pass through this point, 1/4, whatever this coordinate is. We'll then do the exact same thing. We'll follow the tangent line again along that other curve. And the point is that hopefully these two things are kind of close to one another. Okay, so how do we find out what this point is? Well, that's pretty easy. We actually know the equation. We can find the equation of this brown line. So what is the equation of this brown line? Well, it is y. In this case, it's actually really simple because we even know the y-intercept, and we know the slope. So it's y equals 2x minus 1. We're plugging in x equals 1/4. So the y coordinate here is y equals 2 times 1/4 minus 1, which is -1/2. I see. So that means this point right here is at -1/2. Now here's what we're going to do. We're going to consider the particular solution to this differential equation that happens to pass through the point 1/4, -1/2. I don't know what that solution looks like, so I'm going to draw some random function now. This function that I'm drawing here is not f of x. It probably will not have this brown line as a tangent line. It's going to have some other line. So here I'm just going to draw something right now. It will pass through that point, but I don't know what this is. So let's say it looks something like this. Maybe it's probably pretty close to this guy. So I don't know. I'll make it so that it looks something kind of similar. It happens to pass through this point and maybe does some similar things. Who knows? We're now going to find the tangent line to this curve at this point. So I'm going to draw another brown line right here. And picture is not necessarily drawn to scale. So here is my tangent line that I'm going to make right here. And we're going to attempt to find this point right here. We're going to try to find this point, which is 1/2, comma, our estimate to f of 1/2. Okay, cool. So all I have to do is find the equation of this new line that we found here. We need the equation of this new line. Okay, so let's see if we can do it. So let's see. It's going to be y minus, let's see, the y coordinate of the point that it's going through is -1/2 equals, okay, we're now going to need to know the slope at 1/4. We're going to need to know the slope at 1/4, and it's coming from here. So let's see. So the y coordinate at 1/4 of this thing happens to be -1/2. So we're going to have -1/2 squared times 2 times 1/4 plus 2. That is the slope of this brown line times x minus 1/4. This is the equation of that second tangent line right now. And what do we want to know? We want to know what is the y coordinate of this on this line when x now equals 1/2. So we're simply going to plug 1/2 into this, and this will give us our estimate. So f of 1/2, therefore approximately equal to, let's see, -1/2 squared is 1/4 times 2 times 1/4 plus 2 is 1/2 plus 2, which is 5/2. Times x minus 1/4, but x is 1/2, so we have 1/2 minus 1/4, which is 1/4. And then we have to move this -1/2 to the other side, minus 1/2. So let's see here. It looks to me like we have 5/32 minus 1/2. So that ends up being 5/32 minus 16/32, which is -11/32. Now, I do want to note my picture is a little bit off. You can see that I must have drawn this secondary function, this blue function, I must have drawn it a little bit wrong, because we're getting a number that's above the x-axis, but it's actually just very below the x-axis here. And so f of 1/2 is approximately this. Now for the thrilling conclusion of 2013, number 5. In part C, we're actually going to go and finally figure out what this f of x is. So that's what part C says. Let's find f of x exactly. Note that in part B, we estimated f of 1/2. So we'll actually compare what f of 1/2 is, actually is, to what our estimate was at the end, just for fun. Okay, so to solve this differential equation, we're going to use basically the only tool that we have available to us from Calc BC, and that is using the idea of separating variables. This is, in fact, a separable differential equation. Not all differential equations are separable, but this one happens to be, and that's the main tool that you learned about in AP Calculus BC. If you go on to study more math, you'll take an entire class called Differential Equations, where you'll learn dozens of techniques for solving very specialized differential equations used for various things in physics and engineering and other places, chemistry. Okay, so here we go. We're going to try to separate the variables. So my goal is to get all the y's and dy's on one side, all the x's and dx's on the other side, making sure that I keep all the dy's and dx's in numerators, because we're eventually going to start throwing down some integral signs. So here we go. If I do that, we end up getting, let's see, dy over y squared. Dy is in the numerator. I just divided both sides by y squared equals 2x plus 2 dx, also in the numerator. At this stage, the next thing we do is we simply throw down an integral sign. And we integrate with respect to their appropriate variables indefinitely and find the appropriate function. So I'll start with the right-hand side, actually, because it's a little bit easier. So let's see, on the right-hand side, it looks to me like the antiderivative of 2x is x squared plus 2x plus c. And on the right-hand side, we have, let's see, be careful. Common thing kids will want to do is use the natural log here. Totally not necessary. This is just an anti-power rule. This is y to the negative 2. So this is negative y to the negative 1. Negative y to the negative 1. And again, technically there's a plus c that occurs on this side, but we can throw over the constant to be over here. Okay, now actually, we might as well try to figure out what this plus c is, because remember, there is only one function, the particular solution that happens to pass through this point. In other words, when we plug in 0 for x right now, we should get a negative 1 for y. And I actually like to plug it in here rather than solve for y first. It doesn't really matter, but I'd rather do arithmetic than algebra. So I'm going to go ahead and plug in x is 0, y is negative 1. So we're going to end up getting 1 equals, because we have 1 over negative 1 with a negative sign in front of it, 0 plus 0 plus c. So we just found out that c equals 1. Cool. So therefore, we can go ahead and rewrite this. Now that we know this fact, we can go ahead and solve this for y. So if we do that, it looks to me like we're going to get y equals negative 1 over x squared plus 2x plus 1. Which, by the way, I believe is negative 1 over x plus 1 squared. Note that this is our function f of x. That's what we just found out. This is our function f of x. Note that f of 0 is in fact negative 1. And why don't we, just for fun, let's figure out what f of 1/2 is. So it turns out, in fact, then, f of 1/2 was really negative 1 over 1/2 plus 1 squared, which is 3/2 squared. Negative 1 over, what's that going to be? 3/2 squared is 9/4. So negative 4/9. What we estimated it to be, I believe it was it negative something 30 seconds, negative 11 seconds or something. I think that's right. That's pretty close. I mean, if you multiply the bottom by 4 here, you get 36, which is close to that, and you're going to get negative 16, which is close. So I don't know, we're pretty close. In any event, that ends this problem.